In this video, I will discuss the background for Chapter 10 on ordinary differential equations initial value problems. So the first question that you might ask yourself is, what is an ordinary differential equation? Now, an ordinary differential equation, or ODE, well, that is an equation containing a function, y of x, where x is an independent variable. And in practice, very often this independent variable is time, but it can also be, for instance, a spatial coordinate or so when you're looking at a specific example. So we have a function y in that equation, but also its derivatives, its first derivative, maybe its second derivative, or even higher order derivatives are also present in this equation. And that's what makes it into an ordinary differential equation. The fact that it is ordinary means that there are no partial derivatives to multiple independent variables, but that's outside of the scope of this course. So we will focus only on ordinary differential equations. Now, the solution to such an ODE is not a number, but rather it is a function y of x, such that the equation, the differential equation, holds, such that you have your predefined relationship between the function and its derivative, such that that holds. Now, there are several classes of ordinary differential equations, first order, second order, even higher order, linear or nonlinear, homogeneous or non-homogeneous, and with constant or variable coefficients. And well, which class of ODE you're dealing with, that will greatly determine the solution strategy that you will need in order to solve these problems. Not only from an analytical point of view, but also from a numerical point of view. How to solve such ODEs for specific cases by hand, so analytically, that has been one of the topics in your calculus courses. But you've also probably noticed that, well, analytical solution of ODEs can often become impossible very easily. So even for this rather innocent looking ODE over here, you cannot find an analytical solution. So again, similar to what we saw in numerical integration, it is very easy to come into the situation where a numerical solution of your ordinary differential equation is the only viable option that you have. Now, let's look into ODEs in practice, because they are encountered basically anywhere whenever change or dynamics are quantified. And that's something you will find very, very often in any kind of engineering or scientific application. The language of the world, the language of nature, I think would be mathematics, but even more specifically, probably differential equations. For example, here we have an engineering problem where we have a vessel which contains an initial volume of water, and we have an inflow, so a mass inflow Q in, and we have a mass outflow Q out. And now we want to find out what the height of the water column in this vessel is. And for that, we can use this differential equation over here, which basically says that, well, the change in height of the water column is 1 over the density of water multiplied with the cross-sectional area of the tank. And you multiply this with the difference in and outflow, mass inflow and mass outflow. This gives you a differential equation, which you can try to solve then for this function h of t, which quantifies the height as a function of time. Another example here, for instance, is a mass spring system, where we have a mass that is attached to a wall using a spring. And then we can use Newton's second law by stating that the mass times its acceleration is equal to the sum of forces. And the forces enacting on this mass are the gravitational pull downwards and the restoring force of the spring upwards. So this gives us a second order ordinary differential equation for this function y of t, which is the position of that mass. So we can try to solve this second order differential equation for y of t, and that will give us the position of that mass. But also from, for instance, a chemical perspective, here we have a bidirectional chemical reaction with reaction rates K1 and K2. Well, then we can write down some chemical kinetics equations for the concentrations of each of the constituents of this chemical reaction. And this will give us, well, in this case, three equations, one for the concentration of nitrous oxide, one for the concentration of dibromide, and one for the concentration of this product over here. So this gives us a system of three differential equations, which we can then solve for the unknowns, so these concentrations which are functions of time. Let's now turn to a rather simple ordinary differential equation. So this differential equation, which is also called the test equation sometimes, reads as follows. So we have a function y, and this ODE tells us that the derivative of the function y with respect to its argument x is equal to lambda, which is a constant, multiplied with the function y itself. Now you can try to solve this by separating the variables, or you can use various other techniques, but it's quite straightforward to see that solutions to this equation will be of the form y of x is a constant times an exponential function. So then this exponential function has e to the power lambda x. And indeed, if you differentiate this with respect to x, you will see that out comes lambda times c times this exponential. So this ordinary differential equation holds. So all solutions will be of this form. Y of x is a constant times this exponential, where c is an undetermined constant at this point. So this characterizes an entire family of solutions to the ordinary differential equation. Now, if we supply, in addition to the differential equation itself, if we supply an initial condition, so for example, we say that y, whenever x is 0, has this prescribed value y subscript 1, well, then we can simply plug that into this original form of the solution over here, and we can see that this results in a single solution. So if you plug in x is 0 over here, well, this becomes 1. So we have y of 0 is equal to c. So c has to be equal to y subscript 1. So adding an initial condition, one initial condition to this first order ordinary differential equation results in a single solution function. Now the combination of an ordinary differential equation with appropriate initial conditions, that is what we call an initial value problem. And in this case, well, our initial value problem consists of a first order derivative, and then we have a function of possibly x and y, and we have such an initial condition specified at a specific point x is equal to x1. That's an initial value problem. Now we will use those terms, initial value problem and ordinary differential equation, interchangeably in this lecture, but just keep in the back of your mind that they basically boil down to the same thing, only that an initial value problem is also equipped with a specific initial condition. Let's take a look at a slightly more complicated ordinary differential equation and try to get a geometrical perspective on what this actually means. So in this case, well, we have the following. We have this first order equation. So the derivative of the function y with respect to x is equal to x times y. Now again, we can analytically solve this. You can do separation of variables. So push the y to the left-hand side, push this dx to the right-hand side, and then it's quite easy to verify that the solutions will be of this form. So this is a first order and linear separable ordinary differential equation, so you can solve it by separation of variables. And solutions will be of the form constant times e to the power x squared over 2. And you can verify this by taking the derivative of this function. So if you do not know how to find this solution, then I suggest you review chapter 2, or you review the final chapter of your calculus course. But so solutions will have this form, and then by supplying also an initial condition, so saying that this function y for x is 0 should equal a number, a pre-specified number y subscript 1, we can come down to a single solution of the initial value problem. So here the initial value problem would be this ordinary differential equation combined with this initial condition, and which yields this single solution. Y of x is y subscript 1 times this exponential of x squared over 2. So that's the analytical point of view, but let's try to get a geometrical perspective on this as well. So what does this actually say? Well, what this quantifies is that the derivative of the function y with respect to x should always be equal to x times y, whichever the values for x and y are. So we can actually take a look at the xy plane, and at every point in this xy plane, we can draw a triangle like this. Because this is what basically this ODE is telling us. This says that, well, for every point in this plane, if we have a function that satisfies this ordinary differential equation, the derivative of that function has to be equal to x times y. So we can draw these kind of arrows, which indicate that the function should always follow these kinds of arrows, because those lines are, by the definition of a derivative, those lines will be tangent to the specific function that satisfies this ordinary differential equation. So by drawing a triangle with a width of 1 and a vertical height of x times y, we get this kind of tangent field, which is also called a direction field. And this will give us a geometrical point of view of the ordinary differential equation. Because, for example, if we now specify a specific initial condition, and here we have, for example, an initial condition y subscript 1 is 0.1, so that is this red point over here, well, then we can basically trace out how this function will behave by simply following the lines of the direction field. And here I only drew a finite amount of arrows, obviously, but you can draw an infinite amount of arrows by increasing the resolution. But what would happen is, well, if you zoom in on this closer and closer, well, you can always see that the real solution of the ODE will follow these arrows, will follow the direction field everywhere in this XY plane. Also, well, this shows us what happens when we change the initial condition. So for example, let's say that we take an initial condition of y subscript 1 is minus 0.5. That means that we start here at this point, and then following these arrows, we find that the geometrical qualitative view of the function will look a bit like this. And the analytical form of that function is actually, well, that's just plugging in minus 0.5 into here. But we have here also a geometrical perspective. And we can do this for any kind of initial condition that you want. So just by looking at this direction field, well, we can have a general qualitative geometrical point of view of how solutions to the ordinary differential equation should look like. Now, in the previous example, we were able to find an analytical solution to this ordinary differential equation, but I already mentioned that this is quite often not possible. But we can always draw this geometrical interpretation. So here we have in this plot on the right, I just drew these triangles, where in this case the direction field is governed not by x times y as in the previous one, but here it is the cosine of x times y, and then your direction field looks somewhat like this. So what this is telling us, well, that no matter where we start, let's say we start at y is equal to 0, the function will look somewhat like this. It will follow these lines, and that gives us at least a qualitative point of view of how solutions to this ODE will look, even if we cannot analytically quantify or analytically describe those solutions. And this concept of a direction field will come in handy later when we discuss numerical methods as well. Turning to the numerical solution of an ODE, or an initial value problem, well, instead of looking for an analytical function y of x, which satisfies this equation along with this initial condition, well, we approximate this analytical function using discrete points for an interval x going from the initial value of x, here is a, where a is quite often just simply equal to 0, up until a pre-specified time horizon b. So for a numerical solution of such a problem, well, before we start solving it, we have to say, well, we want to solve it from x is 0 to x is 10, for example. So that's what we do over here. Let's say that we have, well, that this would be the exact solution to this problem, where y of x is not really known. I just draw it here such that we can get kind of a graphical interpretation of what this means. And we want to solve the ordinary differential equation from x is 0 to x is 2. Well, then what we do is, well, simply similar to what we did in numerical integration, is we partition the total horizon from 0 to 2 into subintervals, where here I will make 4 subintervals. And this results in 5 points where we will try to evaluate this function y of x. And then using a numerical method, well, we start from this initial condition because at x1 we have that y of 0 is equal to y1, and that is specified in the initial value problem. So this point here, the first point, is known. But then, based on whichever numerical method we're using, well, we will have to find values for y2, y3, y4, and y5. So again, we pre-specify these x points where we want to approximate the function y of x. And then based on the numerical method that we will use, well, we'll have to find formulas for how we come up with y2, y3, y4, and y5. So that is the general strategy of the numerical solution of ODEs. So starting from an initial value problem, an ODE, an initial condition, we will come up with a sequence of points, of combination of x points with corresponding approximations of the function y of x at that point x2. So this will generate a large amount of approximation points for the function y of x. And how we do this is dependent on which kind of solver that we're using. And there's different kinds of solvers. So let's talk about the main classes of ordinary differential equation solvers. And the first distinction that can be made here is on single step versus multi-step solvers. Now, single step solvers, well, they work such that they compute the solution in the next interval using only information from the current step I. Whereas multi-step methods, well, they will compute the solution in step I plus 1 using multiple previous steps. Also, there is a great distinction between explicit and implicit methods, and what this means in practice will become much more clear later. But for explicit methods, we will be able to write the approximation of the function y in the next step, so y subscript I plus 1, as a function of all known values. So x subscript I is defined by yourself. X subscript I plus 1 is also defined, as we previously discussed. And this y subscript I is also known at this point because you computed it from the previous step. So this y subscript I, either you're in the first step and then it is known, or you're in one of the subsequent steps and then you've already computed it. So these are all known values. And so in an explicit formulation, you can directly evaluate this from this expression over here. So that's because you have an explicit formula for the solution in the next approximation step. Whereas for implicit methods, this is not the case. Here we will write the numerical scheme in such a way that, well, you cannot come up with such an explicit formulation, but we still have this unknown value y subscript I plus 1 in the right-hand side over here. So this will require us to solve this equation, which in practice is most of the times nonlinear, because if it were linear, you could recast it into this form. So this will require us to solve a nonlinear equation for this unknown value y subscript I plus 1. That will be implicit methods. And we will discuss the advantages and disadvantages of explicit versus implicit methods in the remainder of the lecture. Let's talk about errors. And we will talk a bit more about errors when we look at specific numerical methods. Now, errors, well, we always said that they are a combination of round-off error and truncation error. And here in this case, well, we will talk mostly about truncation error. And it is important to note that because of the iterative, stepwise, sequential nature of these numerical methods for ordinary differential equations, these errors start accumulating. So here on the left-hand side, we see that whenever we take one step of such a method, well, we will make an error because this red dot is not exactly on the blue curve over here. And this is what we call a local truncation error. So that's an error that we make within one step, assuming that we started from the exact condition. Whereas if we continue proceeding with our sequential steps in order to approximate the function y of x, well, we keep on making such local truncation errors in every step, but also we carry along the accumulated truncation errors from previous steps. And then after a while, this accumulated truncation error will be the dominant, will play the dominant role in the total error that we're making. So that's also very, very important here that we take into account that we carry on those errors from previous cases. And as you see over here, these accumulated errors can result in a error which in the end is quite large. A last thing that I want to say about single-step methods. So single-step methods is probably going to be the main focus. Well, that is the main focus of this lecture, is that we can easily interpret them from a graphical point of view. So the idea is to, well, compute the y subscript I plus 1. So the numerical approximation of the function y of x at x is xi plus 1. So that is here, will be based on the current step. That is the definition of a single step method. And we will do this by, well, increasing xi with h, where h is a predefined or a chosen, let's say, resolution that we have over here. And we will update then the solution based on the current solution plus this length that we project into the future. So this h times a certain slope. Now, the slope will be computed using, for example, we will compute this using f of x and y, because this quantifies the exact tangent of the exact solution to the problem. So using f of x and y, we can make approximations to this slope. And how these slopes are defined, well, that is different for different methods. And that will become much more clear when we look at specific methods. But it's good to keep this in the back of your head. So this kind of picture, that for each of these methods, what we do is, well, we simply update the solution by taking the old value and adding to this a resolution multiplied with a slope. Let's talk about the focus of this chapter in 2W and 50, what we'll be looking at specifically. So first we will discuss methods for solving first order initial value problems, and initial value problems of this form. So a first order derivative is equal to a function of x and y, and we have this kind of initial condition. We'll discuss only single-step methods. So multi-step methods, although they are being treated in the textbook, will not be elaborated in these lectures and are also not part of your exam material. The single-step methods that we will discuss is Euler, as well as modified Euler, and you will see what those are in the next video. We will talk about the midpoint rule for solving ordinary differential equations. And also there is a video on Runge-Kutta methods. Again, as I stated in the previous video, Runge-Kutta methods are not really part of the course material that you have to study for the exam, but I believe that a discussion of solving ordinary differential equations is not complete without at least mentioning these Runge-Kutta methods. We'll discuss how to extend these methods to systems of ordinary differential equations. So if you have more than one ordinary differential equation and more than one function that you want to find, but also to higher order ordinary differential equations. And again, this is not explicit exam material, but it's rather straightforward, and I believe you should at least know about it. We'll finalize this discussion with the question of how large can we choose this resolution, this step length h, which is the difference between different discrete values of x, where we approximate the exact solution using our numerical method. And there will be concerns of stability, and we'll discuss what that is later. But also stiff equations will come into the picture there, because for stiff equations, it turns out that for most of the standard numerical methods, this h can only be chosen to a very, very small value. And we will look at ways in which we can circumvent that in the later in these videos.